in the past month in summertime. So the arithmetic site here is construction which point out to one of the major work of Alexander Grothendieck in the late 50s, early 60s, which is the notion of topos. So topos is a generalization of the notion of topological space. So it recasts in it the theory that in algebraic geometry we study and work with, like scheme theory or various site that we use, Zarinsky site, Tal site, crystalline site. So it generalized the notion of topological space by using mainly the idea of sheaves theory and category, in fact. But it's easy to imagine, following the definition, so what is a topos? A topos, in general, it's a category of sheaves of set over a site. And a site, in turn, it's another category together with a topology. An easy example is the case of a scheme in algebraic geometry for the Zarinsky topology, in which you have the site given by the open set of this topological space. You fix a topology. There is in topos theory, there is a natural generalization of the idea of what we call covering sets for the open set of a topological space. And then, so once you are given a site, then you pass to the topos by considering, first of all, the topos of pre-sheaves on this site, and eventually pass to the corresponding topos of sheaves. It turns out that for a topology that we use in this work, which is the chaotic topology, the notion of pre-sheaf and the notion of sheaf coincide. So, for example, it depends on which topology you work with. This chaotic topology is the topology for which, given an object in the category, the only covering family for this object is the object itself. So it's the roughest possible topology one can impose on a topological space, on a site. And so for this topology, the two notions of pre-site and site coincide. So if what I wrote in these first slides is taken as much as possible following SGA4 notation. In SGA4 notation, one uses, for example, starting with a small category. In this case, the small category is the category, so let's go a little bit step by step now. So then one starts with the natural numbers, the set of non-negative integers, and then we also use the notation n cross, and n cross here denotes the monoid z greater or equal than 0. So n cross is an example of a small category, but a rather particular example of a small category because it has a single object. And dot, you see this bullet in the tech notation. But there are the important information, it's put in this description of the morphism and n cross, they are n cross itself. So J is the chaotic topology, and n cross, we have a single object here, means to say this chaotic topology that the only covering set for the dot is the dot itself. So it's like an information which is not kind of revealing, but the endpoint here was to find an algebraic geometric interpretation of a non-commutative space in a non-commutative geometry, which is the Adele class space, or more precisely, a factor of this Adele class space in the case of the rational numbers. And so the Adele class space is a non-commutative space, which is rather intuitive that the topology you want to give, if you want to find a topos which is connected to this non-commutative space, then the topology that you have to impose on the site, it's something which is weird, sufficiently weird, and not the usual type of topology that we might have in mind. So anyway, here is the notation of usually given, as I said, a small category C, in this case, C's and cross. You have the notation C hat in SGA4 to denote the top of pre-sheaves on the site, which is n cross J. But in this case, for the chosen topology, then the notion of the symbol say C hat or n cross hat, it's the same as what in SGA4 is called C tilde. So C tilde usually is in SGA4, it's the tilde notation refers to the topos of sheaves of set associated to a given topos of pre-sheaves. But this is a detail, but in case one has in mind a certain notation of SGA4. So here is the element here. The topos is a category, so the elements are sheaves of set on this site. And so an element, for example, I mean, you see I call it X here. It's a contravariant functor, so n cross, it's a sheaf, so it's a contravariant functor for n cross two sets. In this particular case, because the category has a single object, then the information of this sheaf is completely recast by stating that I give a set, which is the image of dot, so x dot, on which n cross act following Grothendieck on the right. So because of the contravariance of the functor. So then over this, here we have the x n hat cross, but then you choose, as happened in algebraic geometry, you choose the structure sheaf. In algebraic geometry, you choose the sheaf of regular function on a topological space. And so in this case, we choose the fundamental object in this topos. It's what we denoted n bar. So bar here refers to the fact that this set, this n has in it the infinity. And here it's a major change of the idea of the addition, because the addition is not the usual one. The addition is the inf of this smash between two elements. So this is the major reinterpretation of n, because otherwise if you impose the same addition, you go not that far. So this is one of the several structure in tropical geometry, people use in tropical geometry. Actually, they play mainly, to my knowledge, more on R rather than N or Q. So in this case, anyway, it's a tropical semi-ring. So this tropical semi-ring, it's a particular example, view in this form, is a particular example of a set on which N acts on the right. And in fact, it happened that it has more structure. It's a semi-ring, not only a set. So this is the idea. And the main definition, so the starting point of the definition of the arithmetic site. Yes.
And the main point is that multiplication acts by isomorphisms. Yeah. I mean, this is the crucial point.
Yeah. So then the main definition, so act by multiplication, which is the ordinary one, yes. No right or left, it doesn't matter. And the main definition is that the arithmetic site is the datum given by this topos, which replaces a schema, and the structure sheaf on a schema, which is replaced by the fundamental object in this topos. So n, the pair of n hat cross and n bar. So that then, when in topos theory, because it's a generalization of what happened for topological space for schemes, so one has certain notion, the very general, the idea is to generalize the notion that we found every now and then when we look in scheme theory, for example, at the notion of a point in a scheme. So a point in a scheme, usually it's given by a morphism between these two schemes, the point scheme and the scheme itself. And here, the notion of a point, it's seen in this particular form. So one has to re-understand what means point, single point in topos theory. So single point in topos theory, there is should be a sheaf, should be the sheaf over the point, the topological point itself. So it's, if you are given a pointed topological space, which is a point set topological space, and you look at the sheaf over this point. Then there is an equivalence of categories between the sheaves over this point and the category of the sets. Okay, so point for a topos, in topos theory, it's the category of sets. It's also called the final object in topos. And so we have that the geometric morphism is given by a morphism of topoi, and likewise in the case of morphism in scheme theory between two schemes, well, it is given by a pair of adjoint functors, the preimage, P upper star and P lower star, and they have to satisfy a certain, they are adjoint. So for example, P upper star, it's left adjoint of P lower star. Being left adjoints, it's right exact. But here, it is required more, so not only left exact, but also we impose the fact that P upper star is, right exact, but it's also, we want to be left exact. So this P upper star becomes flat or exact functor in this framework. So a point, in fact, it's at the point seen in this form. A point in the topos and at cross is determined by a flat. Here, flat recasts the idea that is both left and right exact, covariant functor, which is written in this form. So now one might wonder, I start with a contravariant, and then I get a covariant now functor. Well, the covariancy is motivated by the fact that here one usually compose with the Yoneda, the contravariant Yoneda embedding. And so if you compose, so contravariant is this one, contravariant was P upper star, so at the end you can reinterpret this point as a covariant functor. So notice that now it has become covariant, so the action that before for the contravariants were on the right now becomes action on the left. You see in several notation that I use. So for example, if x1 it's a sheaf, so it's an element of this topos, then one can talk about the pullback, exactly like we do in scheme theory, the pullback of a sheaf when it's given a morphism of two schemes, which is now written because these sheaves are nothing but set with an action. So at this point, the pullback, rather than seen like in our terms as a tensor product, when you work with the scheme theory, and then you have rings, commutative rings, and you have a tensor product. Here it's seen in this more, say, elementary form, in the sense that each of these sets, these two are sets with an action. X1 has a right action, and P dot, because it's reinterpreted as a covariant functor, as a left action. And then there is an equivalence relation going on to identify the points, which is expressed in this form. So given x1, element in capital X1 in this set X1, and y, which is an element in P dot, so it's what determines essentially the point. And then, so n and cross act on the left on P dot, because now it becomes covariant. And so then the equivalence relation says that these two pairs, when you move, so to say, the action that you have given here in terms of pk, k is an integer, it's a natural number, to the left, so this is the action which now is moved to the left, and the other side, rather than pky, you have y. So sometimes in books, for example, in McLean, Murdick book, this is called geometric realization. Usually it's also denoted as a pullback. Okay, so the theorem, which is a theorem in SGA4, and reinterpreted in this context, is that a point, in SGA4 you would find a statement in terms of category, small category, etc. But in this case, where the category is this one and cross, so a point, it's equivalent to, in fact, we saw as a flat covariant functor, but now the notion of flat is replaced by an equivalent notion, and I don't want to give, there is a proof, which is called filtering. So a filtering functor in this particular example of the category and cross, it's a functor which satisfies three properties that are recalled here. So for, the first one, it's evident we want to deal with something which has a point in it, so elements in it. So the set X, which is the image of the point, is non-empty. And then, because, as I said, of this particular choice of the topos, the second part becomes as that. So for any pair of points in this set, there exists an element, not necessarily unique element in the set X, and two natural numbers which are now interpreted as acting on Z and giving us X and X prime. So Z is not unique, but for any pair X and X prime in X, you can find a corresponding pair of natural integer acting on Z and giving us the 2 point X and X prime. The third one writes in this form for X in X and two K and K prime natural number, assuming that the action on X given by K and K prime determines the same element in X, then the implication is that then necessarily the two morphisms in N cross should be equivalent, should be the same. Okay, so this is the basic fact which is proven in SGA4 and also reinterpreted in the book of McLean and Mordyke. So here is the first theorem. I will mention 3 theorems perhaps. So this is the first part. So the first part is about the classification of the points of these topos. So the points we saw, they are described in the previous slides. So that we look at the category of points of the topos, which happen to be canonical equivalent to the category of totally ordered groups, first step. And then second step, these groups are not abstract groups, but they are isomorphic to non-trivial subgroup of QQ plus, an injective morphism of ordered group. So, yes. So the way this correspondence goes is rather easy to just to give you, and then I'll give some proof also. So starting with the point, which now is interpreted as a flat covariant functor in this way, then we associate to the point P, script P, H plus, which is the set N cross, which is the set P dot to which N cross act on the left. And then this is a semi-group, and then by symmetrization, you will get H itself. The addition on H plus is given in this form, so it's given through the action of N cross, in fact. So X plus X prime, X and X prime are in P dot. They add in this way, following this rule. So then it's following, as I said, the third property, actually the second property. Let's go back one, remember here, this part. So remembering this part, which is part of the structure of a flat functor, we say that P x plus x prime is determined by the point P k plus k prime z for every z in H plus. Remember that I said that z was not unique. So we choose a z in H plus such that, or in P dot, such that pk z is x and pk prime z is x prime. This is, I'm talking about H plus here, so it's H plus is a semi-group at the moment, then by symmetrization, eventually there is an embedding of H plus in Q plus, which I still have to mention. This Q is, it's the symmetrization, so this is so the story starts with a semi-group, and then by, it's totally ordered, semi-group of Q, and then by symmetrization we get, so I carry on the pair, essentially, of semi-group and then the corresponding group after symmetrization. Then there is the second part. So here the first part already is, in a way, is divided in two sentences, in two statements. First of all, the way to gain a semigroup H plus out of this point. And the second part of the statement is that these semigroup, these abstract groups, totally ordered groups, are in fact embeddable in QQ plus. And then the second part of the story of this theorem is that the relation with the Adele class space, in fact, as I said at the beginning, it's a chunk of the Adele class space because the Adele class space will be this quotient, and then we quotient by the action of z hat cross. So starting with the finite Adeles of Q, the statement says that the space of isomorphism classes of the points in cross, notice isomorphism classes, it's canonically isomorphic to the non-commutative space where Q at cross act by multiplication. How this part goes, because from the first part, you will start with a point, you started with a point, you were able to reconstruct a totally ordered subgroup of Q. Yes, after, you're right. As I said, first it's an abstract totally ordered group, and then there is a way to embed in Q. But then, so this would be the part written here. So to P, I associate PH, where H is this subgroup. Then the statement here is to being able to say that to any H of this type, there is a uniquely determined elements, Adeles, finite Adeles, so that H becomes equivalent, equal to HA, and this is given as a set, as the elements Q in Q, so that once you multiply A by Q, then the output is an element in Z hat. So in this way, the uniqueness of this Adele allow us to conclude that this H is in fact H of A. So there is an A. There is an element in this quotient. And then when you go modulo isomorphism, then you gain this double quotient here. Yes. So you're talking about the
space of isomorphism class is canonical. It's canonical isomorphism. But it's more just a bijection of sets.
Yeah. Yeah.
But the main point is that it's canonical. But at the moment it's just a bijection.
Yes, exactly. Yeah. When you get the point, yes. The blue H. HA, you mean, sorry about that. Yes. Yeah, so this is what I'm going to explain in the proof. So that's the next part, so the statement is coming. So this part says, okay, so let's, I focus first on the first statement. And as I follow from the following result. So the first lemma says, suppose that I have a flat functor, like in the case of a point. The following define a commutative and associative addition on X. So I want to introduce this definition, which is given in the form, essentially, that you see here when a capital F is substituted by script P. And X, together with the addition, which is described here, is the strictly positive part of an abelian totally ordered group, H plus, which is an increasing union of groups ZZ plus. So let's see one hint of the proof. So for example, one could focus on well-posed definition. One could, I won't do that. I'm more interested in to understand why it's associative, for instance, here. So the fact that it's well posed is rather easy, following once again this property which characterizes a filtering functor, especially the property 2. The fact that the addition here is associative, it's a consequence of this fact. So for any finite set, finite is important here in X, via the property that we saw which characterized this filtering functor, there exists a Z in X such that this Z can be described as a subset of this one over which, so Fn cross acting on Z. So it's very important that this Z is finite, because the set is finite. So you can, out of this statement, the associativity follows. Then, for what concerns the question that Lars had, so H plus now is defined to be the set X together with the addition that we have here. And in view of this fact that for any finite set we have such and such here, so this X plus, it's the union, it's an increasing union, in fact, following increasingness with respect to the set capital Z. Notice that given capital Z, finite, there exists a small z which is associated to this capital Z. So here is the increasing union following this idea here of sets which are of this type, because you see in this form, so 1 infinity, it's what gives us Fn cross Z. So then it is re-understood as an increasing union of Z plus in this, because it's generated by a single element, so it's of this form. And then symmetrizing the construction produce an increasing union of groups of this type, Z plus. So here we stress the fact that these groups are obtained by symmetrization of a semigroup, which is Z plus. And the Z plus, in fact, it's isomorphic to each of these. So this is for the reinterpretation of a point in terms of groups now. So from geometry, you have now this way to interpret the points as subgroups of Q. The additive structure on the Hx and the addition determines the action of n cross. So before you could start from the other side of the statement by saying that if I have an x, which is f of a point, of a dot, then the action of n cross on this set is given in this form. The second lemma, it's about the second part of the first statement, where the statement saying that now we want to interpret it as a non-trivial subgroup of QQ plus, so the embedding part. The embedding part it's a consequence of this lemma. So the ordered abelian group, HH plus, is isomorphic to a subgroup of QQ plus, and then eventually there is a second part. For any two injective morphism, there exists, given two of them, so essentially given 2 points, there exists an R in Q cross plus. This is because we look at isomorphic classes of points, so that J primes are J. So this is the part about isomorphic class. So here is now the definition of the embedding inside QQ plus. So here is where we stand before H plus, describing this form, or described as increasing union, or in this form. And so this Jx is determined in the following way, so following this idea. So if we pick up an element in X, small x, there exists a unique embedding of H in Q, so that Jx of X is 1, but where do I send the points which are different from X? Well, I send them accordingly still to the way the filtering functor, the property of the filtering functor. So it is defined in this form, so it's an element in Q, evidently, because K prime and K are natural numbers. For every Z in X, so that what are these K prime and K? Well, there is a K associated to X, and there is a K prime associated to X prime. This follows from the property 2 of filtering functor. And here is the embedding which is chosen. So the embedding, the chosen embedding inside QQ plus, it's again a consequence of these three properties which characterize filtering. Yes, in that. Indeed, yes. Indeed. Yes, left and right exact. And then there is a theorem which says that if you have a flat functor, then it's equivalent to say that is filtering. Okay, so then here is few more sentences about the natural transformation, because the final part of the statement is about isomorphism classes. So a natural transformation of flat functors from F to F prime. So F and F prime are given with by a set with an action in this form, is by definition an n-cross equivariant map. And then the property of flat functors imply that F is injecting in flat. So it's mainly based by using this description of filtering functor. And so here we have, for example, if two elements and X and Y are in H plus, and X, it's as usual, can be written in this form, and Y can be written in this form for the same Z. This is the property 2. Then the addition, after the addition, fx plus y is written, first of all, you write x plus y in this form, and then you use the fact that f, it's a functor, in fact, so to move, and it's a equivariant map, so you move out this f and becomes f prime, because this map is an equivariant map, and then you gain that f of the sum is the sum of the f. Using this path. So then F determines an injective morphism of ordered group, and conversely, you can go conversely on the other side. An injective morphism of ordered group determines a natural transformation of the associate functor. So then the story is that starting with this particular topos, geometric topos, then now reinterpret the isomorphism, the point of this topos in terms of subgroups of Q, which is already a step, because we want to end up inside the Adele class space, or the quotient of the Adele class space. So then the second part, remember the second part of the theorem 1 is about the isomorphism classes of this point are in one-to-one correspondence with the points of this chunk of the Adele class space. So then lemma 3 helps, says that this is the main fundamental, any non-trivial subgroup of Q is uniquely of this form. So I have to describe what is the Adeles here. So in the next slides, you'll see the definition of the Adele, which correspond to this given H. And if A and B determines isomorphic points of the topos, if and only if they have the same class in the non-commutative space. So let's mod out by Q cross plus. So this part is because one look at isomorphism class. Now let's see the definition of the Adele. Okay, so some usual beginning notation. The finite Adeles are reviewed here, and the maximal compact subring. And the fact that there is a way to interpret Q mod Z, as everybody here knows, as a sum over the primes of Q, P mod ZP, following the description of the finite Adeles as restricted product. And so this yields the composition. The composition is the one that is used in the proof that any H subgroup of Q is in fact as an H of A. So we use this simple fact, but relevant, in fact, the decomposition into simple elements. So given a rational number, then you can write this rational number following this idea as an integer, and then there is a sum over the primes. And then these NP are integers, P is a rational prime, alpha P are natural numbers, but there are conditions that you have to impose because you want to end up in QP mod ZP. So NP, it's between 0 and P to the alpha P. And then the NP and P are coprime. Okay, so this is the way, a natural and interesting way to interpret elements, rational numbers. So we will use this in the proof. So the proof of, first of all, the definition of the Adele element. So if suppose you are given, notice that the statement says non-trivial subgroups of Q. So I start with a non-trivial subgroup of Q, and using the multiplication, I may assume that U1 is in H, so means that Z is in H. So then let's see the definition of the Adele at each place. So for a P prime number, AP is defined in this form. So I'm given H, so H is there. I want to link, I want to construct the Adele in a way which connects with this H. So if it happens that for any integer, P to the nu, P to the V, it's in H, then the entry of the Adele at P is 0. If there exists an integer so that P to the minus nu V, it's in H, but not the next power, P to the minus V minus 1, then the definition of the description of the Adele at that place, it's P to the V. So then you build up these elements, this Adele, following the description at the various places. And now the claim is that with this definition, one is able to prove that H equal HA. So I spent the next slides is in fact about the proof of this claim. Sorry, I'm a little bit heavy in this part, but at the moment we published a note in comprendu, and there are no proof. So I do this because so that people see the proof of some part in the note. There was a request, several requests of proofs in these past months. So then let's see this. So we look first at the inclusion of HA in H. So suppose I pick up an element in HA. So it's a rational number which satisfies this property. So for Q in Q, then this rational number will have the denominator, and the denominator is written in a product of P to the J to the alpha J with P to the J distinct prime numbers. So first reduction. Then I say that this Q, in fact, it's an element of QA, so it satisfies this property if and only if you follow now the definition given in the previous slides of the Adele. Q2 times AP, it's in ZP for every P, which means following the definition, so the definition is applied in this case, if and only if A to the PJ times PJ to the minus alpha J is in Z. So there is nothing so deep, so out of the word in this proof. It's only that once it's defined properly, these Adeles, then the thing runs in the way it should. So two cases, if APJ is 0, then by definition of the P to the J, PJ to the V belongs to H for every V. And then the interesting case is when this APJ, notice that this J, it's an index which depends on a corresponding PJ at the denominator of Q. So this is to retain in mind. If A to PJ is different from 0, then it's going to be written as PJ to the VJ. And then one implement again the definition of this Adele. So APJ, so this condition, which is this condition, which is equivalent to the fact that the Q is in HA, it's equivalent to say that evidently PJ to the minus alpha J, so you move the HPJ to this side, and then look at the definition of the Adeles, A. So this means that alpha J is less or equal than VJ, so if and only if PJ to the minus alpha J belongs to H. So then with the implementation now of the simple element, the composition, this fact shows that Q is in H. So and the other part, it's pretty much on the same order of idea, except that one has to implement a Bézout theorem, so to say, to conclude that if you are given an element in H, so it's a rational number, then you get this element, you can see this element inside HA. So here is where we write this rational number in the composition, and you following the decomposition, then there is this condition. A Bézout theorem applies at this in this form to write the multiplication of x VQ in this form, and then conclusion Q is in HA. So there is a unique Adele which satisfies this nice conclusion that H has its own Adele, but up to Z star, yes. And so then the second part regarding the isomorphism points says that suppose you are given two Adele classes here, and they are isomorphism point in the topos if they have the same class in the non-commutative space, because this is what we reached before. Yes. Yeah. Yes. So this is the Adele class space, and then there is a quotient here involved by Z hat cross. So it's a quotient of the Adele class space. No, finite part.
If you take the quotient of the left part, so of HUF by T plus star, then what you get is exactly the non-commutative space of the DC system. So it doesn't have the DC system. But now when you divide by Z star on the right, what it means that you locate on the set term which corresponds to the limit of the data. You will figure out what it is. So that space, it will zero square later, and this is exactly the way it appears. No, the easy part, which is ordinary space when you divide by Z star. That part is easy. That part is final.
There is still the next step when the infinite Adeles are involved, so it's coming. So then two subgroups of Q, they are isomorphic, is by a multiplication with an element. An isomorphism is given by a multiplication with an element in Q at cross. So you gain that if you start with 2 points in this quotient, they define isomorphism point if and only if the corresponding groups satisfy this condition. And then following the lemma, the first part of the lemma 3, then this implies that A, it's necessarily of a B times a certain elements Q, this Q in Q at cross. So that's why we have the quotient by Q at cross, just to pass to isomorphism classes. Okay, so there is a corollary, immediate corollary out of this first statement. The first statement links geometry to non-commutative geometry. And then we saw the points in the Adele class, on the quotient of the finite Adele class space as subgroups of Q. But there is an equivalent way to interpret the category of points in terms of category of algebraic extension of Zmax, which are included in Qmax. So what you look at, you look at all possible semi-fields which are in between Zmax. Zmax is recorded here. It's a semi-field, so it's a Z union minus infinity with the addition given by the max and the multiplication given by the sum. And this semi-field fits in between with a nice intuition that if you look at the smallest semi-field, the case when k is equal to Zmax, then you gain the Adeles, which is in fact an Adele, the Adele 1, 1, 1, 1. So it's like if you started with a commutative point, in this quotient of the Adele class space, the points 1, 1, 1, 1, 1, which has as is associate semi-field Zmax, and you fatten this commutative point, you enlarge, you make a tubular, you make a neighborhood of this point using non-commutative points. And then you gain to the max case, the case when k is q max. This is like a generic point versus a point which is the specialization of each order in geometry. So if you have a point in Lavelle in geometry, you can look at the specialization of this point. And so this minimum point, the point 1, 1, 1, 1 in the Adele class space, in this quotient of the Adele class space, corresponds to the specialization of any other point inside this non-commutative space. Then there is the generic point in algebraic geometry, which now it's reinterpreted as a point associated to Qmax. So just to, as usual happen in algebraic geometry, points, morphism of points in one direction corresponds to the reversing, the maps going to the reverse inclusion for the algebra. Here, that's why there are inclusion in this form. So the generic point, it's the top one. Right? But it's contained in any other neighbor, on the neighbor of any other point. So the morphism are injective morphism of semi-field. And here is the association. Interesting is the association. So it's starting with this point, covariant functor. Then we know that this point has its own H or HA, in fact. And then how to reconstruct the semi-field? Well, you have this semi-group, group H, to which you add minus infinity because you want to be inside Qmax. And so the group itself, Q, was inside Q. The group H was inside Q, but then you interpret it, you add minus infinity, so at least you are inside Qmax. And then, of course, the operation change at this point. So there is a further step saying the operation in H is the traditional one, but it transfers, yes, yes. So this is one way. And the second way, I mean, the way around is, suppose I have this semi-field fitting between Zmax and Qmax. How could I reconstruct a group in Q? So I want to land inside Q, and I'm inside Qmax. So first of all, I intersect with Q to take away minus infinity. And then the output is that modulo a change of operation, then you get a subgroup of Q traditional with the traditional operations, which determines a point, as we saw before, because any abstract subgroup totally ordered, like in this case, subgroup of Q determines a point. So the association are written here, described here. Now we move, so far it was only point on the Adele class space. Now this is the end part of my talk. Now I never implemented in this proof sheaves, structural sheaf. It's like I was looking at this generalized form of topological space and its point. Now the second part, it's about what happened when I implement implement the information of the structure sheaf. What do I gain? In particular, when you have the structure sheaf, people look usually at the stock of the structure sheaf. So it's important to see what happened. What are the stock of the structure sheaf? Why the choice is so important? So the next part is theorem 2, which says that now let's implement the information of the structure sheaf and bar on this on the topos and at cross, and look at the stock. Look at the stock in the way to describe the stock as you have a morphism of topoi between the point, between the Caterina of set and this topos, and you take the pre-image, like I defined at the beginning, or geometric realization. So you look at the stock along this point. So this is happen to be, the description is written here. So this is for the stock at pk. Now each p has its own k associate. So I look at the stock for a p associate to k, and then it's like if I take the pre-image along the morphism of topoi between the point P and at cross. And it turns out that the stock is written in this form, so it's a collection of elements in K, which has the property that the sup between R and 1 is 1. So in particular, this sheaf, the stock of this sheaf, the unit here, it's only 1. So this is a local semi-ring. And the fraction field of this local semi-ring, it's K.
What is important to say from the start is that the stock is automatically endowed with this fraction of semi-ring. This is about because what you have is you have a sheaf of semi-ring, so the stock is automatically semi-ring. And this theorem determines the semi-ring fraction of the stock.
Okay, so why this description? Why the stock has this explicit description? Well, we go back to the definition of the pre-image given at the beginning. It was given as a quotient, remember, with the equivalence relation. So it turns out that the action of n cross on n bar, so n cross acts with two fixed points, which is on n bar, 0 and infinity. Then there is an orbit of 1, which is free action. So keeping in mind this way to realize the action of n cross on n bar, then you have that the quotient and the way you define the equivalence relation. So it turns out that this quotient is in fact divided as a disjoint union in 3 parts. 2 classes of point, which are the class of 0 R and infinity R, which corresponds to the fixed point of the action of n cross on n bar. And then there is a copy for the action of n cross, which is free over 1, so determines a free action. Then there is a copy of pk dot. So this is the description of the stock, but we want to gain this part. So we want to define the map beta connecting this way, which is out of the description of the definition of the pre-image, and this way to interpret the pre-image. So the map beta sends the classes of the two fixed points to correspondingly 1 for 0 and infinity, R is mapped to 0. And then for the free part, which is given by the action, so this class of 1R, it's mapped to minus R. And behind this minus R, because one might wonder, why this minus R at this point? Why minus? So notice that Zmax or Qmax, etc., they have as an addition the sup. N bar as an addition the inf. So the changing of this setup, it's the motivation behind here, this definition, which I do not send R, 1, R to R, but 1, R to minus R. So I repeat the story. So then the point is determined by K. K is in between Zmax and Qmax. In particular, the addition in K is the sup. But then the stock of this semi-ring n bar fills the definition, of course, the sum in n bar, it's the inf. So this change between sup and inf produce this small the minus sign here. In particular, in the case of, if I look at the stock of the point corresponding to this Adele 11111, this is, which is written here, this is isomorphic to n bar, so it's in the map sense n to minus n. Again, there is minus n because of this change of addition, the inf rather than the sup. Okay, so now this is the infinity to R. No, this is the pair. When I say it's the pair. Okay. It's the equivalent class. Okay, yes. So, but essentially, it's. Sorry. No, and also the equivalence class. In fact, it's a single point in this case. So then, final part. So then the role of the finite field Fq here is played by another basic semi-field. So inside Z max and hat R max, there is this basic easy semi-field. Is the smallest semi-field, which is made by the set 0 and 1, with the addition that it's like to say the soup between 1 and 1 is 1. And each time this equality happens, so x plus x equal x, we call it a structure of characteristic 1. So B, it's, as I said, it's inside R plus max naturally, because the soup here is the same addition that we found in R max. So R max has this, at the bottom of R max, there is this element, this semi-field made by two elements. And B also is included in n bar, but the fact that n bar has the addition given by the minimum produce the output that if you look for an inclusion of B in n bar, B notice that the addition is the soup, then you have to define coherently the map, the injection map, sending 0 to infinity and 1 to 0. This is again due to the fact that the two operations, the two additions are different. So it is a general fact in semi-rings that known to semi-rings people that B has no finite extension. There is no semi-field extension between B and Z max, for example. It's not like the case of finite fields that you can build up the tower Q to the n, F Q to the n. Here you jump from B immediately to Z max or to the smallest compact semi-ring inside Z max, which is 0, 1 max. And then if you compute the global section of this structure sheaf for the topos, then you find 0 infinity again. So a set which is isomorphic to B. So very few global sections. And there is but the nice thing is that there is one parameter family of automorphism given by, which is the Frobenius automorphism in this context, sending x to the lambda in R cross plus. And so then, as we do for schemes, so we usually, if you have a scheme defined over some field, you might think in this case a topos defined over B, then you want to look at the points of this topo defined over, you know, the various extension of this basic structure. So there are points that they are defined, for example, for an elliptic curve, which are defined over f p to the n, but they are not defined over fp. It's important to see how the points behave. And so here, because between B and Z max, there are no finite field extension, you have to jump immediately for the consideration of points defined over. You jump immediately from the case of points defined over B to the case of points defined over Z max, or in fact, like sometimes we do in algebraic geometry, inside the ring of integer of a field, in this case 0, 1 max. So then the theorem study this particular idea, the description of the points in various, in the two fundamental extensions of semi-rings. So the set of isomorphism classes of points defined over the local maximal compact semi-rings, so this is like the ring of integers in Z max plus of the tropical semi-field. Sorry, R max. I read R plus max, depending on is canonical projection with this non-commutative space. And the action on these points corresponds to the action of this quotient of the Adele group A cross Q modulo Q cross, but then you always have this, you have to implement all the time this quotient by Z at cross, because it was already that. Yes, it will arrive. Yes, indeed. And then, so let's see. So I want to study this point, the points over 0, 1 max. There will be, as I said, points which are defined over B, and therefore they are defined over Z1 max, and points which are not defined over B, but it becomes defined over Z1 max, R plus max, but in fact 0, 1 max. So because it's 0, 1 max here. So notice that this 0, 1 max, it's local sub-semi-ring. So it's like to study, as we do in algebraic geometry, to study, if you want to study the points defined over various field extension, it's like to study morphism of this type, where here it's spectrum of 0, 1 max, and here is the ring or semi-ring topos. So because this is a map between two structures which are 0, 1 max is a local semi-ring, so it is determined by two parts, as in classical scheme theory. There is the geometric part, so the image of this F is detected usually by a point, and then the corresponding map at the level of section, FP sharp. So FP sharp will go, and this is a reason why we studied the stalks, in fact. FP sharp will go from this side, actually from the stalk of n bar at P, which I denoted OP cross, to 0, 1 max. You go to the reverse direction. But it's a local morphism. So a local morphism, there are two cases. The case where the image of this FP sharp is completely contained in B. So in this case, because it's a local morphism, the maximal idea mapping to maximal idea, then the image will be 0 in this case. And this type of points, it's what we see in the description of this double quotient of the Adele class space. If you think of it in two possible subsets, there is the finite Adeles, the one I consider all the time before. So these finite Adele classes corresponds one-to-one with the points in PPK whose the range of the corresponding local morphism, it's inside B. So the points which are defined over B, over the bottom semi-field, they are in fact fixed by the action of this Frobenius. And then there is the rest. So the rest means those points for which the image of this map is not completely contained in the B. But in fact, the intersection between the range and 0, 1 is not empty. So in this case, you will have to implement what are the corresponding groups. So then these points, shortly, each of them corresponds to a subgroup of this type plus or minus log U for U in the range U not 0. This is a rank 1 subgroup of R. So notice, but before they were subgroup of Q. Now we have the subgroup of R. And the association which links this part to this part is given in the form that if I'm given a pair of a finite Adeles A and an element lambda in R cross plus, this is a way to interpret the double quotient, by the way, this pair is mapped to lambda times HA. Remember that HA was the subgroup corresponding to the finite Adeles. So lambda times HA now becomes, for this lambda action, becomes a subgroup of R. HA is a subgroup. No, yeah. Exactly. So H of A was a subgroup of Q. Multiply, I dilatate, I scale it. And then, so that's essentially why you have these two types of points correspondingly to the decomposition, natural decomposition of the quotient of the Adeles. Final story I want to say now, because the time is over. The interesting part, one interesting part will be when Alain will explain what we were looking at in this summer, because one could say, okay, now I have this topos, which is a algebro-geometric interpretation of the Adele class space. But I'm also interested to connect with the spectrum of the integers, because after all, we want to study zeta function. So it was important to link with the spectrum of the integers in the way of a map of topoi, which Alain will describe, sending a point in spec Z to a particular group, which depends on this P, which I denoted HP. I don't put the definition. Alain will enter in details. So what we have is that not only the construction of this algebro-geometric interpretation of the Adele class space quotient, but also a link with spec Z. So then this map of topoi will allow us to reinterpret the object as the sheaves above this topos. Notice that here I added on purpose 0. So before there was no 0, it was n crosses. And so at this point, the sheaf over this topos are sheaves of semi-rings. The sheaves on this scheme, topos, they are sheaves of commutative rings. But how to work with them? Because they are semi-rings, the other one are rings. So there should be a common basket to contain semi-rings structure, rings, commutative ring structure, also hyperrings, which is a structure that we encounter in this project, in a unified manner, and also to unify certain construction in Arakelov geometry, which are due to Durov, that in a unified way. So the unified way seems to be the way to reinterpret semi-rings, hyperrings, and other structure that pop up in construction in arithmetic geometry of these latest times in the unifying frameworks of sheaves of S algebra. S here refers to the sphere spectrum. So there were two ways to interpret the point. There was the algebraic topological way to interpret the point as sphere spectrum, and the geometric algebra geometric point to interpret it as 0, 1 or B, the semi-field B. But how to unify this construction? How to put together the topological view, which brings up its own information that we don't have from the algebra geometric part, with what we have worked on in the past 5 or 6 years. So there seems to be, and Elena will talk about this, I think, a unified way to interpret by going back to certain construction of Siegel, of gamma spaces as algebra. So I leave the story there, but just I want to underline the fact that it's not only we have the topos, but also a connection to the spectrum of the integer now. Okay, thanks. S is the sphere spectrum. Sphere spectrum. Yes. But it's interpreted in a more elementary form, like not really the spectrum as a collection of spaces and maps, etc. In a more, in the way Siegel interprets spectrum in the 50s, 60s. So Elena will be exhaustive on that. No. It's a way to. My way to think about that. It's a way to fatten spec Z over which the structure, perhaps the structure of spec Z for what concerns trace formula, the zeta function is too tight, to fatten it in using a space which has evident tight link with it, but in which non-commutative geometry is available. So that's motivation.
What happens is that, what we have found is we found the topos, which then explains the chart. The topos is based on the three-dimensional algebra of the empty mode, the star and the center. Now, what happens is that this topos, just applying the topos mathematically, does lead you to the correct non-commutative space or correct space. And now, what happens is the following. What happens is that you can wonder what is the relation with spec Z. Now, spec Z actually maps to this topos, and when it maps to this topos, it gives you where the lecture formula concentrates, when you give the parent problem. So what happens if you want is that spec Z is like the skeleton, where the lecture formula is concentrated. But on spec Z itself,
Probably it's not possible.
Points.
You don't have points.
It's an illusion when you work with finite fields that you are going to the strategy of finance theory to work in the case of number theory. And the reason is the reason is that when you look at the Weil formula, the explicit Weil formula, then the denominators which appear in the Weil formula, they don't appear in the case of finite time. They don't appear because they are equal to 1. So in the case of the number field, they appear non-trivially, there's no way to make them, and they are an indication, this is essentially what Zelda found with this Zelda formula, they are an indication that they are not just the periodic orbits, there is some flesh around them. Okay? And so, I mean, now the space that we found in topos is the topos which has exactly the right geometry properties, and it's not standard. But then what Caterina Consani about, and she's very right about that, is that spectrum maps, it's not like it's unrelated to spectrum, but it's not a tropical relation to spectrum. No. You see, I mean, yes. Where does it map? So, for instance, if we take the point corresponding to a point P, okay, it maps to the subgroup of R, or the abstract group, if you want, of fractions which are the denominator of our.
This is the meaning of HP.
That's the meaning of HP.
The definition.
If you look at it as a subgroup of R, it's not I mean, it's a subgroup of R, okay, the fractions are fractions the denominator of U. Now, what you can see immediately is that why it's the right one. It's the right one because if you rescale this subgroup by lambda, lambda is a positive number, you will fall on the same group when lambda is equal to the power of 2. But if you think of the multiplicative group additively, this means that it has length of 2. So exactly the right one, it has length much. And so this and it is a log P which appears in the explicit formula. So, I mean, okay, like this, you know what could be. So, could you use the curve tropical by saying that you don't look at the integer as the ordinary way, you look at the integer in the tropical way. This is the starting point. Okay? So which means that instead of adding the integer to the and instead of multiplying them, you take the side. So it's a quick header. You have any question? Yes, please. So now you have a zero there. Oh, yeah, the zero doesn't change anything. The zero is just a decoration. If you compute